So we have taken n number of reference point on the chord line first. So we hold the aerofoil at leading edge point. We are changing the angle and we are drawing the curve, CL curve and CM curve. Then we are holding at 25% of the aerofoil. Now we are changing the angle, different angle of attack. The CL curve will be same because same aerofoil, same boundary conditions. Depends upon the holding location. Only this moment curve will vary. Then, for example, I am holding in the trailing edge. Okay, 0 degree, 10 degree, 20 degree, 20 degree, like that. I am changing the angle of attack. Again, CL curve will be same. Only the CM curve will be varying. So, like that, they have taken n number of points experimentally. Then they have taken the CL CM curve, and this type of curve they get it. Okay, see here, leading edge point is around 25%. This is the trailing edge. Whatever the point you vary, the CL curve is fixed. Only depends upon the location. That moment on that location is varying. Okay, this is for leading edge. This is for around 25%. This is for the trailing edge. And in between points, you will get a number of CM curves here. Okay, so 0, 10% of the chord, 20% of the chord, 50, 70, like that. If you vary the point, only this curve will vary, CL will not vary. Is that clear?
Yes, sir.
Okay. And finally, what they have found? So they have taken n number of points, and they found for a particular point that CM curve is just a straight line. Okay, for a particular point, they found the CM line is a CM curve is a straight line. That means this moment is constant. Even though if you change the angle to 0 degree, 5, 10, 15, 20 degree, the moment is not varying. Okay, and that point they defined as the aerodynamic center. Okay, so for a particular point, the moment is constant for different angle of attack. That point they defined as aerodynamic center. Now what happened? This point also, so taken by S. For example, this is 25%. Okay, so I hold the model at 25%. I change the angle to 5 degree, 10 degree, like that I change it. So this point is fixed, and moment created on that point also fixed. Now if you go for the tail design, you see this is the aerodynamic center. The point is fixed. This is at around 25%, and there will be additional moment that is also constant. Now if we find the total moment, it will be lift into this distance plus this moment. Okay, now I have two moments which is constant. Based on this, I can design my tail to create the balancing moment. Okay, previously the center of pressure, it is varying, so it is difficult to design the tail. Now the point is fixed, moment also constant. Now I can get the constant unbalancing moment. For that, I can design the tail to balance the moment. Is that clear? Aerodynamic center. That's why we went for this another one reference point, that is aerodynamic center. Now we'll go to the third point. So whatever the experimental results you check, CLSS alpha, CDSS alpha, and moment curve and all, they will take this quarter chord point, that is 25% of the chord. They won't take aerodynamic center. Actually, we found theoretically aerodynamic center is good, but again, instead of going for the aerodynamic center, they are going for quarter chord point. See here also, this is CM/C/4. Any aerofoil result you see, it will be the moment curve will be drawn at the quarter chord point. That means the aerofoil is fitted at the quarter chord point. The reason is, actually they found that the aerodynamic center is lies closer to this quarter chord point. That is the first reason. For example, assume I am giving you 10 aerofoils. First one is, sorry, NACA 0012, then 2412, then 6412, then 23012, then 63012. Like that, I am giving 10 aerofoils. And we have the derivation for how to find the aerodynamic center. So you are finding the aerodynamic center for the first aerofoil. This may be 25%. For the second aerofoil, this may be at 24.5%. Here it may be 25.5%. Here may be 24.7%. Okay, here may be 25.2%, like that. If you find the aerodynamic center, it will be lies closer to that 25% of the chord. Okay. Okay. Is that clear? So the aerodynamic coefficient center, if you find theoretically for any model, it will be lies closer to the 25% of the model. Another simplification. Okay. Another simplification is, see, if you want to test 10 models, then for every model individually you have to find the aerodynamic center, and exactly at that point you have to hold it. Instead, so they are taking 25% of the chord as the reference point to place the hold the aerofoil. Okay. Initially we started with the center of pressure, then we thought aerodynamic center is better. At last, finally, they went for the 25% of the chord. Okay, because if I give 10 aerofoil also, simply you can go for 25% and you can proceed the testing. You can plot the graphs. So it is easy compared to the other two definitions. So that's why all the graph you see, it is of 25% of the chord. So first reason is aerodynamic center is lies closer to it. Second one is it is easy to take for any aerofoil. And you see this is symmetrical aerofoil. Okay, I think NACA 0012. They have taken 25% of the chord only. But if you draw this moment curve, it is almost constant within the stalling angle. If you see, it is constant. That means for this symmetrical aerofoil, it is 25% only. But if you take the unsymmetrical aerofoil, say only from here to here it is constant, and near the stalling region there is a small deviation. Okay, so this 25% is again like an approximation. It is not accurate method. For approximation only we are taking 25%. For symmetrical aerofoil it will work perfectly, but for unsymmetrical aerofoil there will be a small deviation in that moment, but it is negligible. Is that clear? Any doubt? So we have to find the location. Tell me, someone started something?
No, sir, no doubt, sir.
Okay. So location is very important. So at last we end up with this 25%, which is more or less accurate, and it is easy to fix for any aerofoil. Okay. So now we will go to the derivation of aerodynamic center. So before that, this is one basic. So this is the CL curve, and this is the CM curve. So within the stalling angle of attack, it will be like a linear line. So we can find the slope of the line. So the lift slope, if you take, this is dCl divided by d alpha, and we are denoting that as A naught. Okay, so lift slope means A naught, which is dCl by d alpha. Similarly, for this moment curve also, we can find the moment slope dm by d alpha or dcm by d alpha, that we are denoting as m naught. Okay, in that upcoming derivations and all, we will use A naught, m naught. Why is okay? We will use, okay, it comes A naught and m naught. That means lift slope and moment slope. This is just basic. Now we will start with the derivation. Again, here also we are going to compare ideal case and real case. In the ideal case, I am placing the force system in the aerodynamic center. Okay, so this is normal force, axial force, and this is not the center of pressure, so there will be additional moment. That is the moment about the aerodynamic center. Okay, the distance is XAC, that is aerodynamic center location from the leading edge. I am writing in terms of chord. That's why it is CXAC. Okay, and already I told you what we have to find is this distance. Then the only one equation is which relates this known forces and this unknown distance is the moment equation. So I'm writing the moment equation about this leading edge point. That is minus n dash into CXAC plus this additional moment. This is the first equation for the ideal case. Then for the experimental, because we don't know this n dash a dash and all, to find that we are going for the experimental analysis. So we have to fix the aerofoil at some reference point. We are taking 25% as the reference point. So through that we are finding normal force, axial force, moment about that point, etc. and all. Now again we can write the moment equation. So n dash into, there is minus n dash into c by 4 plus m dash c by 4. So both are same aerofoil, same angle of attack, same velocity, then the force will be same, then the moment created by the aerofoil is same. Then for these two cases, the moment is same, equal. Is that clear? These two cases. It is almost similar to the center of pressure, ideal case and real case. There also we have taken, if you see, there also we have taken ideal case where we placed it center of pressure. Then real case we have taken the quarter cut point. Then we compared this moment. Similar way, here also we are taking ideal case at aerodynamic center, real case at quarter cut point. Any doubt in this slide? Hello? Okay. So I equated both moment equation. This is the final one. Here if you take, so through the experiment, assume we found n dash and this location is fixed. Moment also we found at the quarter cut point. And this side equation, if you see, again we know the n dash c, and we have two unknowns. We don't know what is the distance and what is the moment about that aerodynamic center. We have two unknowns, so it will be difficult to solve. It is not like the center of pressure equation. So here I am going to apply another one condition, that is aerodynamic center condition. So what is the condition for aerodynamic center means? The moment is constant for different angle. That is dm by d alpha is 0 or dcm by d alpha is 0. Okay, so this condition I am taking it. So I am going to rearrange this equation for m dash AC. Okay, so rearrange this equation for m dash AC. That is, these two terms will go this way, and simplify, you will get this equation. Okay, same equation, write it for m dash AC, remaining terms, you rearrange, you will get this. Then I am going to convert moment into coefficient of moment. So simply divide by q infinity c square both side. Okay, so here cc get cancelled. So this is n dash divided by qc is cm. This is cmac and this is cm c by 4. Is that clear? This slide. Just equated, and I found there are two unknowns. So I'm applying the aerodynamic center condition, that is dcm by d alpha is 0. So write this equation in terms of MAC, convert that into coefficient of moment. Now this is my final equation in terms of coefficient of moment. Now we have to apply that condition. Then what you have to do, we have to differentiate this equation with respect to alpha, d by d alpha on both sides. You will get this equation after differentiating. Now I am applying another one simplification. I am assuming the angle of attack is small, that is less than 7 degree. In that case, Cn is equal to Cl. Okay, so instead of Cn, we can write Cl. Okay, so this time is 0 according to the aerodynamic center location. It is 0, and instead of Cn, it is Cl. And this dCl by d alpha is A0, already I told you, and this dCm by d alpha is M0. Now you rearrange, you will get this excess equation, 1 minus 4 minus M0 by A0. And I think center of pressure, if you take, it is 1 by 4 plus or minus, what is the term, we got it? Minus only, right? Where it is minus. This is for center of pressure, and this is for aerodynamic center. So two equations. Is that clear? The center of pressure, aerodynamic center derivation. Hello?
Yes, sir, clear.
Okay. And another one point, if this is the airfoil and CLCD curve, center of pressure means at every angle you have to find it because it will vary. Okay. But this aerodynamic center, it won't vary. At any point you can find that will be constant, aerodynamic center, right? That's why instead of finding at this high angle, we are trying to find at the low angle, so that instead of Cn, we can substitute Cl. Normally in the experiment, they will give alpha, Cl, Cd, etc. and all. Once you know Cl, Cd, you have to find the Cn, then you have to substitute here and find. But whether you find it on the high angle or low angle, that aerodynamic center location will be same only. So further we are simplifying. We are trying to find only at the low angle where Cn is equal to Cl. That's why we simplify. So in the center of pressure, there will be two equations. One is in terms of Cn, another one is in terms of Cl. So Cn is for high angles, Cl is for less than 7 degree low angles. Okay, but here we are trying to find only at the low angle, and that will be constant. Wherever you find, it will be same only. Is that clear? So this location is fixed. Aerodynamic center location is fixed. That's why we aim for this point. It will move only to the small percentage, then the 28%. Okay, it lies closer to the 28%. It's a fixed point. So as it is the fixed point, you can find at any angle of attack. You can find at 2 degree, 6 degree, 10 degree, 15 degree. You will get the same value. So what we are trying to find at the small angle of attack itself, because the calculation takes only one step. Otherwise, you have to find the Cn, then this formula you have to come.